So the next talk will be on inefficient temporal graphs, and Jason will give the talk. Thank you.
Thank you. So thank you very much for having me present here. So my name is Jason Schoeters. I'm in my second year of postdoc now, and this project was, or this subject rather, was started about 2 years ago, but it was just a side project. And then 1 year ago, my then boss over here in the middle, Eric, gave me permission to have an intern on the subject. So and so we continued working on this a little bit since then. So this is unpublished for now, but we aim to publish maybe by the end of the summer, at the latest the end of the year. So we're going to talk about inefficient temporal graphs, which is a bit unusual because normally we would like to build efficient temporal graphs or recreate efficiency. But so this is to maybe get a bit of a two-sided view. Yes.
Yeah. I cannot see the slides. We have to
oh yes, I didn't think about sharing the slides.
Okay.
Of course. So I need to join the link, of course. This one. Or I could just send the mail and you can open it here. Is that fine?
That's fine.
To where is it?
So we don't have mail access here, so that's a problem.
So how did? Okay.
You have your talk. It's a PDF.
Yes, it's a PDF.
Okay.
Can you not log in?
Oh yeah, good. Thank you. I completely forgot that I should share my slides on the meeting. Should be this one. This one?
Yes. Oh, it's on D directly. No, it didn't work. Didn't copy.
Was I too quick?
Or maybe.
Jason, if you click here on the link,
Yes.
what happens?
It asked me for an email address to log in, which maybe I could have just
Shouldn't that?
put, but
Can you try again?
so yes.
Can you go to the website?
So should be copied now.
And removed.
Yes, there we go.
There it is. Okay.
Oh, are they?
Yes.
Go ahead.
This one, right?
Yep, should be good. What is full screen? F12, Control L. Good. So most of the time I start my talks with some context on temporal graphs, but I don't think you need this in this workshop. I believe you have maybe better context than what I usually present. So I'll just skip this part. And well, you all know what temporal graphs are, but just that's this video, right? That's this video.
No, with the video over there, but
okay, that's fine for me. Yeah. But so just to make sure we're on the same page about what kind of temporal graph I'll be using in this talk. So most of the time I use this representation, which is a graph with some labels put on the edges, which are going to represent the times at which this edge will be present during the lifetime of the graph or of the temporal graph. So there's another form to represent this with as a series of snapshots or static graphs, and both, of course, correspond to each other. In this case, I will use the name or the term footprint to describe this graph without all of its labels. So a static graph, which is also the union of all these static graphs over here. I will use the term journey or temporal path for the analog of a path over time in my temporal graphs. So in this example, I usually give this one, where a temporal path or journey starts from this vertex and then continues to go here, and then finally reaches its destination at the final time step. And of course, that journey is also present over here with 0, 1, and 3. And we've probably talked about this already before during maybe the Spanner talk. We like to consider this special type of connectivity in temporal graphs, which we refer to mostly as temporal connectivity, which is when, so a graph is temporally connected when all pairs of vertices can reach each other through some journey. So let's get into some more details concerning this specific talk. So we're going to be talking about the temporal graph design problem, which is in its most basic form represented as this. You're given a graph, a static graph, also called the footprint or the, I've heard some other words this morning. So the static graph, and then we're going to put some labels on this static graph until we attain some desired property, which I've denoted here P. So let's look at some examples of this property P, which have been studied. So one of the earliest properties that have been studied was this one, where you want to label your graph until you have temporal connectivity. I would like to do this with as small amount of labels as possible. For example, with 2n minus 2. So here n is the number of vertices of your graph. And so this is quite easily done. You just take your input graph and you design it so that you have all of the smallest labels, so 1, 2, 3, 4, and 5, which creates sort of an inward going tree and up to some vertex over here, for example, which collects all the information of the graph. And then afterwards, you do the same, but the other way around with 6, 7, 8, 9, and 10, so that an outwards tree disperses again all this information. And so this graph will be temporally connected with at most 2n minus 2 labels. You can actually do a bit better. When you look at 5 and 6 here, these two edges play the same role, so you can remove one of them. So you can attain always 2n minus 3. You can do even more, or even less rather, but this requires for there to be a C4 cycle in your graph, which is not the case in this input graph. So I cannot show you. And then lastly, you can prove that 2n minus 5 is impossible. You cannot create a temporally connected graph with only 2n minus 5 labels. So this is basically derived from some work done in the 70s, which is based on gossip theory. It wasn't called temporal graphs at that time yet. So that's old work, but recently, some people, so Metzels et al., studied this problem of trying to minimize the labels in some graph design problem, but also while trying to limit or minimize rather the lifetime of your designed graph. So they've had some nice results, including some graph classes where you have to choose between one or the other. And also related to these temporal graph design problems, but a bit different this time. Enright et al. Were studying this problem where they were giving the graph and they were also given the amount of times every label has to appear. And then they would have to choose the ordering in which these edges appear so that the reachability is minimized. So now you don't want to attain temporal connectivity, you want to try to minimize that. And so a remark I had with regard to all of these temporal graph design problems is that all of them, they try to either minimize the number of labels that you want to assign, or you are already given the amount of labels that you have to assign. So I was thinking, well, what if we do the reverse? So sorry, let's take this temporal graph design problem with the minimization property. Let's redefine it as follows. So let's just call it sparse labeling problem. Given a graph, can you assign a labeling such that your graph becomes temporally connected with using at most some given k labels? So I wanted to study the reverse problem, dense labeling problem, where I wanted to ask, can you assign at least k labels such that your graph is temporally connected? And so most of you should be thinking now, well, of course, you can just take the densest graph possible, a complete graph, and assign the whole number line on every edge. To avoid this kind of trivial problem, and also in terms of motivation, you can see that a lot of these labels are not going to be necessary for temporal connectivity. They're just going to be there for no reason whatsoever. So in other words, when you remove one of the labels, the graph is still going to be temporally connected. Yes. That's a good question. I'm going to answer that in the next slide, I believe. So at the moment, you can just say, think one or the other. So we have to redefine a bit our question to make sure that this trivial example does not answer it. So we're going to have some definitions. And I was surprised to see that this morning someone already used the necessary keyword. It was for an edge, I believe, not for a label, but it's the same idea. So we say that the label is necessary if the reachability of your temporal graph is reduced when you remove the label. And then you can continue with that. You can say that a labeling or even a journey or anything else is necessary if and only if it only contains such labels. Or another way to put it, you cannot remove anything without breaking temporal connectivity. And also in this talk, we will be talking about proper labelings. So this term means that all edges will have distinct labels. This is to avoid some questions of, can you cross multiple edges at the same time or not? And so, yeah, putting all of these definitions into the problem gives this. Does a proper necessary labeling using at least k labels exist, such that your graph is temporally connected? So most of the time, I just say that this is a nice theoretical question to try to answer as a motivation, but sometimes you would need more than that as a motivation. So you can see it as a sort of game where you would like to play against or you would like to play against some verifier and try to put the most labels possible on some graph. And this can represent maybe trying to waste precious network resources of your adversary. And also in terms of spanners, which was already talked about this morning, these represent the worst case scenarios. So when you cannot obtain sparse spanners, for example. So this is to address the question of George. We're going to introduce these kind of measures, or rather, first we're going to present the measures which already exist, and we're going to extend those. So in terms of measures of a temporal graph, we have these. So first, temporal cost, T, is the total amount of labels in your graph. Okay, the most natural measure, I would say. But then you could also be interested in a more localized measure, which is the maximum number of labels on some edge in your temporal graph. And we're going to denote this with the tau. And so we're going to extend these. No, we're going to give an example first. So here, two temporal graphs, this one and this one. Here, the temporal cost of this one, just to make sure we're on the same page, it's 3, because we have 3 labels. Same is on the other side, we have 3 labels here. Both are of temporal cost t equals 3. However, they don't have the same temporality. This one has temporality 1 because there's at most 1 edge or 1 label per edge. And over here we have temporality 2 because there's this edge with 2 labels. So let's extend that for a static graph now. So we say that maximum temporal cost, t plus, is going to be the maximum temporal cost of any temporal graph you can construct using necessary labelings and the footprint which is given. And the same thing is true for maximum temporality tau plus. So another example, this graph over here, just a simple K3. What would be the maximum temporal cost of this one? Well, we saw before this labeling. So we can just put that labeling over here. That would be a temporal cost of 3. And you can prove that that is actually the maximum you can do. However, for the maximum temporality, tau plus, this labeling does not suffice. You can actually put this labeling in, even though this labeling is not on the K3. You can still just ignore one of the edges which is given in your footprint to obtain the temporality or maximum temporality 2. So the main question I would like to answer in this talk and in this work is how high can t plus and tau plus go? So we have some bounds on it. The lower bound is quite trivial. You can just take any paper on temporal graphs, try to find the labeling in the paper. And most of the time, they're either going to have 1 label per edge, or maybe some will have 2 labels per edge. Maybe even some others have more labels per edge, but then it will probably not be necessary anymore, or maybe I've missed some papers. So the lower bound is 2 for now. And the upper bound on how high you can have a tau plus is n minus 1, and this is proven in the following way. If you have an edge E over here, on which you're going to have a lot of labels, then you can already have the argument, well, since in your graph you're going to have a lot of journeys going from one way to the other. As a reminder, we're in a graph that is temporally connected, so we're going to have a quadratic amount of journeys going everywhere. You can argue, well, maybe all of these journeys have to use E. And so there's going to be a quadratic amount of labels maybe on this edge. And that's sufficient to prove that the upper bound is quadratic, but you can do better. So in this example, let's focus on one vertex, which is going to be this one. And let's focus on all the journeys that go outward from this guy to all of the others. You can maybe think, okay, well, maybe they will all use this edge E. And so since there's going to be a linear amount of vertices, maybe there's going to be a linear amount of labels on this edge. But you can think a bit more carefully about this. So all of these vertices, or all of these journeys rather, will have to come through this edge at different times. So there's going to be some ordering, which I've put on the bottom among these labels. And now I can just say, okay, no problem. I just keep the lowest label, the smallest label. Because then I know, okay, you can already reach this edge and be here at the lowest label possible, and then just wait until all of these other journeys that go from E reach all of these other vertices. And so that argument gives at most one label per vertex in the graph. And since these two vertices don't really, I mean, these are adjacent, so one for these two is enough. So that gives the n-1. For T plus, so the temporal cost, maximum temporal cost, we have this annoying, not annoying, beautiful rather, labeling of Axiotis and Fotakis, which we have talked about before already. And so when you count the number of labels that are used in this example, you get this 1/18 n squared. So that's the lower bound. Maybe we can go higher. We will see. And as an upper bound, I just took this n-1 and multiplied it by the number of edges you can have in a graph. It's cubic, but I believe you can probably bring it down to quadratic, although I haven't succeeded in doing that yet. So yeah, let's see if we can. So these are going to stay like this for the rest of the talk, but we're going to see if we can push these up. And if not, well, let's maybe take some families of graphs and see what are going to be the maximum temporality and temporal cost. Sorry. So I'm going to start with the simple case, which should state on the top simple case trees. So for trees, we're going to actually be interested first in the temporality. And so in the temporality of some bridge edge. So take your bridge edge, represent it like this. If you take it away, the graph is disconnected by definition. What's going to happen here? Well, we're going to put a lot of labels on it. And we're going to assume by contradiction that all of these are necessary. And at some point, we're going to prove that you can remove almost all of them except maybe two. So there we go, a lot of labels. Let's assume all of these are necessary for maybe some journeys. So let's first consider all the journeys from going from the left side to the right side. Okay. And so again, there's going to be some ordering over here. And we can see that we don't need all of these labels. This is not a necessary labeling. We can remove some of these labels over here because we know that since the graph is temporally connected, the latest vertex which can reach this edge, which is going to be the black one, which is this journey over here, we can just keep this journey. And then all of the other vertices have to wait at edge until this guy arrives, and they're going to hijack the black journeys, which are going to reach all of them over here. So that's the argument which says only the latest label is necessary to go from left to right. And then you apply the same thing, but going from right to left. And these are the two labels which are going to be necessary on a bridge edge. You cannot force more than two necessary labels. And so as a direct implication from that result, you have that for any tree graph on n vertices, the maximum temporality is 2. And when you apply this result on the multiple edges that you have in your tree graph, you get that the maximum temporal cost is going to be 2n minus 3. So this minus 3 is due to the fact that we're in a proper setting. If you use proper labeling, if you use some other labelings, maybe this is going to be 2n minus 2. And so, yeah, so I said we're going to try to see if we can push this maximum temporality as high as possible. But here I just proved you, well, for trees, it's going to stay 2. So is it even possible to have necessary labelings where the maximum temporality is more than 2? That's a first question, which I tried to answer and which I had some preliminary results on. So we're going to construct exactly this case where we're going to have an edge with temporality more than 2, let's say 3. So this edge. And then we're going to have to make these necessary. They're not at the moment because you can just remove any 2. But let's try to make them necessary for now. So 10 is going to be necessary for the journey U1 to V1, etc. And now all that's missing is trying to make this graph temporally connected without breaking the necessity of these labels. So I had to find some way to do it, but in the end, I found this graph, which is necessary, or rather the labeling is a necessary one. And so this is a graph with maximum temporality, or this temporal graph has temporality 3. So we know that it's possible to push this to lower bound. And in fact, this can be generalized. You can just add another triplet like this on the bottom, and another one, and another one, and another one. And each one of these triplets will force another label on the top. And so that already pushes the lower bound for a maximum temporality to 1 over 3n. But maybe we can do more. And also, as a side note, the temporal cost of this is also a bit more than Axiotis and Fotakis' counterexample. The bit more is hidden in the big O of n. I think their example was 1 point something n, and this one is 2 point something n. So it's not very noticeable. But we are pushing these bounds up. So all the work I've presented until now, I've already presented these as preliminary result at the Dash tool 2 years ago, I believe. Maybe 3 now, I don't know. And Malte Renke, who was also at the Dash tool. So this was during the open problem session. And he joined in and he said, well, what about this labeling? And so let me just clarify what this one is. So you take a cycle and you assign to every edge all the odd numbers up to n over 2. So in this case, I believe n is 10, maybe 12. Yeah, 12. So you assign all odd numbers up to 6 on some edge, and then you skip an edge and you assign them again, again. So maximum matching of these odd labels. And you do the same thing, but this time with the even labels. And this does generate a necessary labeling. So you cannot remove any of these labels without breaking temporal connectivity. And as a result, this odd even alternating labeling allows for temporality 1 over 4. So worse than the one we just saw before. But in terms of temporal cost, it just skyrockets from 1 over 18 to 1 over 4. And so this is what made me think, well, okay, trees and maybe the ad hoc construction from before doesn't allow for relatively large values, but this cycle apparently does seem to allow for very large values. So can maybe something more be done in cycles? And so that's where the internship of Esteban began. We wanted to do a lot of stuff, but one of the things that we wanted to do was extend STGen, which is a generator from Arnaud Castet, which he used in his work on temporal spanners and clicks, in temporal clicks rather. So this is a generator which generates happy labelings with some pushing, very pushed techniques. And so we adapted it. I don't have too much time, so I'll skip these details, which are very interesting in its own, but don't have too much time left. So the result from his internship, among some others, were that we enumerated all necessary labelings of cycles of size up to n equals 14, which isn't a lot, but for temporal graphs, this can be quite a bit of number of labelings. And we found some very dense labelings, one of which we were able to find a protocol for. So this is the protocol that we found. It's quite difficult. Again, not too much time, so I'll just go quickly over it with this example. So you assign all of the odd numbers up to, I believe it's n, all the odd numbers up to n. On some edge, this is going to be your edge of maximum temporality. And then you go to the even numbers and you distribute them. So 2 here, 4, 6, 8, just skip. And then you do more or less the same thing, but at each step, you're going to put the smallest label on both edges. So here, 1 is on both edges, then 2 is on both edges, then 1 and 3 are on both edges, then 2 and 4 are on both edges. And also you're removing some labels that are high as well. But you continue doing this, and then at the end, you do more or less the same with some extra condition. And this labeling produces a temporality of 1 over 2. So as a reminder, we had 1 over 4 from Malte's labeling, 1 over 3 from the ad hoc construction, and now we have 1 over 2. So this is the best one found until now. And also, as a nice side result, which I didn't notice until Timothée told me in Bordeaux, the temporal cost of this labeling should be more or less equivalent to Malte's. So I did the math, and it's actually beating Malte's by exactly 1 label, which is huge. So yeah, and so this theorem is easy in terms of counting the labels, but you'd also have to prove that this works for every n, that it's a necessary labeling. These were the difficulties of proving it. And I was planning on going into details how we used another perception of temporal graphs, which is called the link streams, more or less the link streams from, for example, Latapi et al. And so I defined some new kind of journeys where I said, okay, these journeys, whenever you go from a Cn, so I think it's over here, yes, the proof ID that this is necessary is by induction. You start with proving that this is necessary using this special kind of journeys. And then the inductive step from Cn to Cn plus 2 is, well, these stream links, you just add another layer on it every time you go plus 2. And these layers are very useful in the sense that you can prove that these only serve to make this special kind of journeys one longer. Which makes all the Cn plus 2 obey our previous lemma as well. But again, I don't, maybe you're not following, that's normal because I didn't have time to go into this. I misjudged a bit my time, sorry. So as a last step, we used our labeling to have some results as well in cactus graphs. These are going to be similar to the ID at the start, where you have an inwards tree and an outwards tree, except now you don't go to some vertex, you go to the largest cycle in your cactus graph. So you have your inwards tree going to your largest cycle. You use our labeling, and then you have an outwards tree. And so this is also a necessary labeling, and it produces these results. You get a temporality, which is literally the 1/2 from the previous, but in this cycle, and you get some temporal cost as well. So these are the theorems again that we've talked about up till now, with some corollaries on how to get some more results from these. So the tree graphs extend to connected graphs, the cycle graphs extend to Hamiltonian graphs, and the cactus graphs extend to any graphs of some circumference. And so all these bounds hold. And so in terms of future work, there's some things you could do. I would have liked to do this first one for today, but I wasn't able to. So the idea is to lower the upper bound of n-1 to 1/2n for cycles, because in our experimentations, we always got 1/2n. So maybe it is always 1/2n. And so I tried to do this by showing that by contradiction, if you have more than 1/2n labels on some edge, you can remove one of them. And I tried to do this by studying some forbidden configurations of this special kind of journeys I talked about. Okay, so this workshop is focused on algorithmics, and I didn't really talk much about algorithmics. So a very natural question is, well, is this problem even NP hard to compute this maximum temporality? And then you can talk about different type of labelings, but that's also something else. Thank you.
So time or any question?
Can you hear me? Okay. I'm kind of interested into a value with a strict setting where you say tau plus is greater than 1/2n empirically. No, the one above.
Oh, this one. This is, as I said, there's a question mark, and I mean, I didn't say it, but as I noted down here, there's a question mark, and empirically, this just means that the generator that we constructed, or labeling generator, we extended it as well in multiple ways, and one of the ways was to consider strict labelings.
Yes.
And it spit out some labelings which beat this 1/2n. So that's why I put this down over here. Maybe there's some constants at play since it's just experimentations.
So you do not have any idea of why it would be like this?
I do actually have an idea. So I should have used the board a bit more, but that's okay. So if you have, for example, this graph, and you're in the proper setting, you cannot force 4 labels on this one. You can only force 3, maybe 1, 2, and then 3 again. But when you're in the strict setting, you can force up to 4 labels here by doing, and now I suppose this is necessary, and it has 4 labels.
Yeah. Okay.
Maybe that's a reason why you can beat the 1/2.
Any other question?
Can you somehow combine this with some other ideas of distance measures? For example, just thinking of the very stupid one without any restriction, say the number of time steps you have. I think currently you are not limiting this.
You mean the lifetime of the graph?
Yeah,
The largest label used?
yeah.
That's a good idea. So it kind of reminds me of the work from Mercios et al. As well, who tried to do the same thing, but for trying to minimize the labelings. So that might be a next step. But at the moment, there's still a lot to be done here without trying to minimize or I suppose you want to minimize it, the lifetime. So yeah, maybe that's a bit too soon, but then again, prove me wrong. So
Okay, thanks.
Any other question? Okay, let's think Jason again.